Hello, this is a little video that's an extension of the last video, which is going to be on electron configurations and orbital diagrams. Now, as I mentioned, went through basically one or two examples of these electron configurations, which is a schematic way of showing how electrons orientate themselves around an atom. So basically, if we have our nucleus in the center, we have our energy levels, and we're looking to see when and where they drop in. And this electron configuration is just another model which is attempting to explain how things work. Now, it may not seem like it, okay, but this model it's more different than it is difficult. And once you figure it out, it is quite straightforward. Now, for the situation here, we have what's called an orbital diagram. Now, I'm gonna be leaning on things from the last video. So let's say, for example, I want to do nitrogen. Okay. Now, nitrogen, I'm gonna do. Okay, we have total here of 7 electrons and 7 protons because we're neutral. But either way, so 7 electrons. So I'm going to do 1s2, 2s2, 2p3. Now I'm getting that from the periodic table, and I start building from the hydrogen atom and start working my way across. I have the s orbitals, I have the d orbitals, which are offset by 1 from the row, and I have the p orbitals, and I have my f orbitals located right here. F orbitals are offset by 2, meaning that this is the 6th row, but this is a 4f. This is the 7th row, but it's a 5f. So again, this is a real simplistic video, and it's difficult to maybe convey all my thoughts, if there's no one there to ask questions. But this is the first energy level, second energy level, third energy level. Okay, we're talking 4, 5, 6, 7. Of course, this would then run right down to that guy by a little break. But this is the 4th row, so this is 3D. 5th row, this is 4D. Okay, this is D1. Either way, as we run through this thing, I'm looking for nitrogen is right here. So it's really kind of easy to get to. So at the beginning, 1s1, 1s2, that's this guy and this guy. 2s1 and 2, so that's this here. 2p, 1, 2, and 3. Now, whenever I do a orbital diagram, I start with an electron configuration. So I'm going to read. This wouldn't be included, just so you know. And below here, I would include the number of orbitals. Now, for the orbital diagram, we're going to include 2 more principal quantum numbers. The electron configuration only shows the principal, the orbital, and the magnetic, and the spin. So in this case, what are they? We will recap this again. This is the energy level, and it's symbolized by N. This is the orbital diagram, symbolized by an L. This is the magnetic. This is, now again, a little more about this is the suborbitals. All right, and then we have the spin, which is going to be spin up or spin down, plus 1/2 or minus 1/2. It really doesn't matter how you look at it, up and down. Let's back up here 1 minute. Okay, let's take a look at this. Let me give myself a little more room here. All right, so for the magnetic, okay, now for the magnetic, of course, all right, so we have the orbital quantum number, which is L, and we have the suborbital. This is the number of orbitals, and this is a spin. So with the orbital, let's say we have orbital number, principal quantum number 1, which contains an s orbital. So that would be actually labeled as 0. So the s orbital is labeled 0. The L, or the p orbital would be labeled 1, and the d orbital would be labeled 2, and the f orbital would be labeled 3. At that point, the suborbital is the number of subs. So an s orbital contains one suborbital. The p orbital contains 3 suborbitals. This guy contains 5 suborbitals. This guy contains 7 suborbitals. And each suborbital can hold a maximum of 2 electrons. It can hold less. So 2, 6, 10, 14. These are the number of electrons. So this magnetic orbital number, which is written as an L with a little s, so an S would be an M, is going to represent the number of suborbitals and which one it is. So we often describe these numerically as, so this is the number system for the L, and then for the magnetic it would be 0, again the 1 suborbital, and then this guy has 3 suborbitals, would be plus 1, 0, and minus 1, plus 2, plus 1, 0, minus 2, minus 1, minus 2, 0, it's going to be plus, so we've got 7 total, so plus 1, plus 2, plus 3, minus 1, minus 2, and minus 3. So 7 total, we have 5 total, we have 3 total, and I have 1 total. So now, knowing how many suborbitals they have, and then knowing that in each suborbital it can hold 2 electrons total. So the way this works is, let's go ahead and show this. We have below here, I list out, you can do a box like this representing the suborbitals. This is 1 suborbital, which technically would be 0. And then I have this suborbital here, which is 0. And I have, this guy has 3 suborbitals. I would say 0, plus 1, and minus 1. Now, this numbering system, sometimes they use letters and different things, but this is pretty much as easy as you can get just by labeling it. Now, inside we have 2 electrons. Each electron is represented by an arrow. Now, arrow up or arrow down, it really doesn't matter. Okay, just that they have to be opposites. Arrow up and arrow down, arrow up and arrow down. Now, when you get multiples, okay, we have to fill separately first, and then if in which everyone's full, we can come back and we can match up. This is referred to. This is describing. This is the end of the orbital diagram, by the way. But this little bit right here, filling in separately, is called Hund's rule. Okay. And that's pretty much it. This is my orbital diagram. If I were to do another one, okay, let's try another example here. Let's do iron. We'll do Fe. All right. See if that fits up there, and it does. All right, so iron, I did this example for the electron configuration, so let's do something different here. Let's do, all right, let's do nickel. All right, now nickel, in fact, let's do zinc 2 plus. So zinc 2 plus is one that's going to have a grand total of 30 electrons for zinc, and since it lost 2 electrons, it's going to be 28 electrons. So first thing to start off with is an electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now I'm jumping the D range, 3d, and normally zinc would be 3d10 for 30. I'm going to do 8 here instead because I lost 2 electrons. Now, number of suborbitals, 1, and I might just put a bottom part of my square. 1, this guy's got 3, this guy's got 1, and this guy's got 3, this guy's got 1, this guy's got 1, 2, 3, 4, 5 for the d orbital. These are the number of houses in your suborbital. So in this case, 2 electrons, arrow up, arrow down, arrow up, arrow down. Again, up, down makes a difference, but when they're together, they have to be opposite. And these will all fill in separately. And again, even the individuals, it doesn't matter. Arrow up, arrow down, arrow up. I could put this one in first, this one in second. Just they're all going to fill in eventually. Arrow up, arrow down, and even here, it doesn't matter which ones I fill in. They're all equal energy-wise. So I need 8 of them. So 5, 6. Let's pick the 7, and let's go 8. These 2 are left empty. Okay. This is the orbital diagram for zinc. You could do a shortcut method for this. It would just be zinc 2 plus, and the previous noble gas to zinc is argon, so we put argon in brackets, and I start from there, and that's just going to be 4s2 and then 3d8, and of course it would just look like this. It would be the back half of it. I'll extend my line a little here. 1, 2, 3, 4, and 5. And in this case, I will do that. I still have my electrons. I'll have the top 2 blank in this time instead. And this is the orbital diagram for zinc 2 plus ions. A few things I just want to highlight here. Every single atom will get assigned a set of numbers. Every single electron, I should say. So, for example, like this electron right here would be the third energy level would be 3. D orbital. Now, like I mentioned in the previous slide, okay, D's are assigned a number 2. All right. So D is 2, and then at some point you can number these 0, plus 1, plus 2, minus 1, minus 2. But essentially they're all equal, so each number could be assigned differently. So you need to say it has to be something relative. So plus 2 is within range. I couldn't go plus 3. And then arrow up or arrow down. So arrow up or down, or it doesn't make a difference. It'd be plus 1/2 or minus 1/2. These would be sets of quantum numbers for that electron, or it could be technically it'd be an electron in the outer level of zinc 2 plus ions. And finally, we have a thing called the Pauli exclusion principle. Okay, it says that no 2 electrons can have the same set of quantum numbers. All right, so these numbers that I assigned to that particular electron belong to that electron and not a different atom. Within an atom, you can have this, not have 2 electrons that have the same quantum numbers. All right. Thank you very much.